Right, ready to do the next stage now. I've got my table of results here and it's time to plot the graph. Now, the first thing that I need to do is ensure that I'm going to use more than half the graph paper by selecting a good axis or a good set of scales for my axes. And the way that I need to do that is I need to use more than 6 squares here between my lowest point, which will be on the log t values, it will be minus 0.276, and my highest point, which is going to be minus 0.016. They're going on my x-axis, so I need to choose an appropriate scale. I need something just below minus 0.276 and something just above minus 0.016. The values that I'm going to use are minus 0.30 to go on the bottom of my y-axis. That's just below minus 0.276. So I'm going to put that in here. Minus. The reason that I'm writing on this side of the paper, by the way, is because my x-axis values are going to count down in that direction. So minus 0.30. I'm going to use 4 large squares to be 0.1. So this is minus 0.20. This is minus 0.10. And this is 0. Now 0 is just above 0.016. That should allow me to fill up as much of the graph paper as possible. I should use more than 6 large squares. I can't leave my scale like this. I need to make sure that at least every third large square, that's 3 large squares there, have a label on them. And in order to do that, I'm going to put the value in here, which is minus 0.05, and then here minus 0.15 and minus 0.25. Now every 2 large squares are labelled, that's fine, because that's more than the minimum of 3. The x-axis, which is log m, I need a value just below minus 0.699. Minus 0.7 springs to mind immediately, and then a value just above minus 0.155. If I go from minus 0.1 to minus 0.7, that might do it. Let's see, so if I started at minus 0.1 here, 0.2, 3, 5, 6, 7, well, that's 6 large squares. I only need 4 in this direction between my 2 points, so that'll probably do it. So I'll put those values in there. So that's 0.1 to 1 large square. Okay, don't particularly need to label that here, but I will. Right, now I need to plot my points. I will start with the lowest one here. This is minus 0.699. Now I need to plot to the nearest half of a small square. That's my minimum accuracy. So I'm going to plot it as carefully as possible now. This is going to be practically on the thick line, so that'll be alright. And this is right down here, minus 276. This is minus 2.25. And this would be minus 0.275. So I'm going to be just beyond there. So if this is minus 0.275, then 2829. So 275, and that's minus 0.28 go just halfway along that small square. So I'm going to put my point here. Okay, first point. Second point, minus 0.523. So 5.2. Okay, so 0.52 is just to the left of the second small square there, and minus 0.180. So we've got 0.15. Now every 4 small squares here is equal to 0.01, so 0.19, 0.18. My value is 0.180, so it's going to be exactly on that line there, that second square along. So you can use a ruler, makes life easier. Just beyond there. Okay, that's my second point. Then minus 0.398, so that's just alongside 0.4, and minus 0.127, so this is 0.11, 0.12, that's 0.125, so 1.127 is going to be pretty much on there. So go here. That's alright. Okay. 0.301, so again pretty much on that 10th square there, and 0.086. So 0.08 is going to be 4, and then another 4. So that's 0.08, then 0.086, going to be just over halfway, so about there. So plot there, I think. Yep. Okay, nice and clear points hopefully, and 0.222. Now this 0.22 is going to be over here, so I need to go 2 on from the 0.2, and then 0.041. That will be just 4 small squares away from 0.05, so that'll be there. He's going along here, and then 2 squares along. Maybe just a little in there, but I only need to go within half a small square, so it is nearer that square, and that'll be okay. The extra to the third decimal place. Okay, last one, 0.155. So 0.15 is there, so I'll go halfway along that for the 5 on the third decimal place. Then 0.016. Okay, so 0.01 is 4 small squares, and then if I go halfway along, which is another 2 small squares, so there will be alright. Okay, so those are my 6 points. 1, 2, 3, 4, 5, 6. Okay, should label my axes. This is log T, this is log M. Okay, divided by the units. The precision to which you label these does not matter. That's quite okay, even though the precision is different in my table. That's okay. Line of best fit now. need equal number of points above and below the line. So if I plotted there, I've actually got 1, 2 points above and none below, so I'm going to alter. What I'm trying to find is what's the best trend of points to follow. I haven't got any point. I haven't got 5 points making a nice straight line, so I'm going to need to just go with a fair scatter of points around the line. So I'm going to go for that. Let's see what I've got here. I've got 1, 2, 3 points below, 1, 2, 3 points above. It's a fair scatter of the points above and below the line, so that's okay. Let's see how good my trend of data is. Well, these ones here, they're clearly within 4 millimeters, so those 4 there, they're okay. This one is just over 3 millimeters away from the line. That's within 4 millimeters, and that one is as well. You can see that by eye. So B2.3, that mark is for having a good set of data. You need 5 points within plus or minus 4 millimeters of the line, which I've got, so that's okay. Alright, so that's my graph, that's what it looks like. The next thing to do is to work out the gradient of the line. So I'm going to choose 2 points on the line. I need to make sure the hypotenuse of the gradient triangle is more than half of the line which I have drawn. Okay, let's use this point here. It seems to be lining up with graph grid quite nicely. And I'll point up this end. Well, you can use that one there, that's lining up reasonably well. And also, now what I'm going to do is write on the number of those points. That's 1, that's 0.1 there, and this is 0.2. So you're counting left to right, that direction. Okay, coordinates of this point then. x1 is minus 0.7. y1 is, so this is minus 0.25, 0.26. This would be minus 0.275. So this is minus 0.27, and this one is minus 0.273 or 25. Okay. So those are the coordinates for this. Had a slight disruption there. My phone got called, so stopped filming. Right. I've just found out the coordinates for the first gradient point, which is down here. I need to find out the second gradient point up here, the coordinates for that. So x2 is minus 0.2, and y2 is this is this is minus 0.05, and this is minus 0.025. That would be minus 0.030. So this would be minus 0.035. Let's just verify that. Minus 0.03040, minus 0.030, minus 0.040, that's up to minus 0.05, so yeah, that's okay. Back to this sheet then. gradient is y2 minus y1 over x2 minus x1. So y2 minus 0.035 minus, and it's a negative, y1 is, so minus 0.2725 over minus 0.2 minus 0.70. Calculate that, and then we've got the gradient. Okay, calculating. Reciprocal. So the gradient is 0.475. Right, y-intercept, y equals mx plus c, c is equal to y minus mx. Now that will apply to 0.1, so I'll take my y1 and x1 values, that's these two here. So c is equal to minus 0.2725 minus 0.475 times by x1, which is minus 0.70. So times 0.7 and then need to add that on. So minus 0.2725. So that gives me 0.06. I should check, given that I've calculated that, looks like a sensible value. There's 0, so it's going to be crossing in the positive region. I've got positive value, so that looks sensible. That's my y-intercept. Next thing to do is to do the analysis. This is the page for doing the analysis. I have an equation, t equals cm to the power of n. If I flip back here, you notice I've got log m against log t on my graph. So I'm going to need to get this equation into a form involving log t and log m. So I'm going to take log off both sides. So log t will equal log c m to the n. I'm going to use the first log rule. I have two terms here multiplied, so I've got a product of c and m to the power of n. That means that I can write out log c plus log m to the power of n. So that's the first log rule. If you have a product of two terms inside the log, you can write that as the log of the terms added up. And the third log rule can also be used here to simplify this term, which will be, so firstly log c. Now when it's m to the power of n, I can bring the n down and multiply it by the log of the term there. So that will be plus n times log to the power log of m. Okay, so that's my equation then. Log t equals log c plus n log m. I need to compare this equation to y equals mx plus c. My reason for that is that I've plotted the graph and it's a straight line. So therefore I can use the equation of a straight line, the general equation, which is y equals mx plus c, to compare with this equation that I now have, which is the log of that particular line. So if I write that out again, log t is equal to log, I'm going to write the n times log m first, plus log c. If I write y equals mx plus c under here, so you notice this method I'm doing is I'm not taking a point from the line now and substituting it into this equation and doing any calculations with it. I'm using a different method, which is comparing it to y equals mx plus c. Again, back to the graph. Log m is on the x-axis, so the x quantity is log m, and on the y-axis I have log t, so that is my y quantity. And you'll see it's lining up quite nicely here. I have my y quantity, my x quantity here, and therefore this, whatever is multiplied by log m, is my gradient, and the added term here is the y-intercept. I'm going to write down what they are here. The gradient is equal to n, and the y-intercept is equal to excuse me, log c. It's a good idea to do that because I've got two c's here. I don't want to confuse those. Excuse me. Right, this needs a little bit more work done on it. So this equation, the inverse function of the log is to raise 10 to the power of the quantity. So the left hand side would be 10 to the power of y-intercept, because I'm doing both things, same thing to both sides of the equation, and that equals c. So if I inverse function the quantity c, or the term c, then I will get the c by itself. It's like multiply and divide is the opposite function. That's my equation. Now I'll calculate the values. No need to calculate n, it's just equal to my gradient. So over here, 0.475. And 10 to the power of the y-intercept. Let's get my calculator. Okay, so 10 to the power of... That is 2 point... Well, let's write it out here. 10 to the power of 0.475 is equal to 2.99 if I leave it to 3SF. So I've got 2.99 and 0.475. This marking point here, there's two marks available here. The first one is actually for the y-intercept. Oh, I didn't write down my y-intercept. Oh, I did write it. Okay, which is 0.06. So I'll get one mark if I did the y-intercept correctly. Second one is for recognizing that the y-intercept is equal to log c, which is this part. So you see I've written it down here. Always a good idea to write down what the various terms of y equals mx plus c is equal to. And I also, in addition to that, I need to determine a suitable value for c, which would be this part, so calculating that and then stating it there. that's what those 2 marks are available for there. One of these marks is for recognising that n is equal to the gradient of the line. So again, I've written that and stated that clearly here. Gradient is equal to n, and then stated the value. So that's one of the marks. The second mark here is determining a value of k. I need to rearrange this equation here for k. So starting with that equation, if I rearrange it, root k will be equal to 2 pi over c, square both sides, k is equal to 4 pi squared over c squared. Put values in, so 4 times pi squared over 2.99 squared. That's 4.42. Alright. You also need to have stated k to an appropriate number of significant figures, so I've stated it to 3. That's okay. 3SF or 2 was what was expected there, so that's okay. 4.42 is my value of k. And that is the analysis. Just trying to remember back to see if I covered the justification of the significant figures given for t. Just to recap that, usually this justification of significant figures, this question here, that normally appears at the end, and you would justify how many significant figures you'd stated for k or perhaps c. But in this case it was justifying how many we'd used for t, and you had 2 options for justifying those significant figures. First route is you take exactly how many decimal places you had in your raw time. So I used 10 oscillations, so that would be 2 decimal places here, giving me 3 significant figures. So to the full dp, that's 2 dp and 3 SF. So 3 SF there, and you can carry that forward to your value for the time period t. So I can use 3 SF here. Now the way you would phrase that is something like this: 10 SF was measured, 10t, or little t if you like, little t representing the full length of time that I measured, was measured to 3 significant figures. So 3 significant figures was carried forward, or 3 significant figures were carried forward to t. So you could use that. Second method is to use your reaction time. If you use this method, you need to actually state your times according to reaction time. With reaction time, if I write them over here, what I'd have is 10t1 be 5.3 seconds. So I'm going down to 1 decimal place. 10t2 was 5.3 seconds as well. So I now have 2 significant figures. Probably a good idea to get used to the idea of stating minimum number of significant figures, because often you'll have a mixture. So I've got 2 significant figures, and then you can carry that forward to t. That would be 0.53. That's 2 decimal places, but 2 SF. Okay, and so you can say something similar as we did here, which would be t was measured to 2 significant figures, so because of the human reaction time, so 2 significant figures were carried forward to the time period t, and that would be the justification. that's now all of the points covered there.